Okay. Your second until yeah, until the screen here is appear. Okay, we'll start with the theory of Eigen problems. Was the topic today's Eigen problem that is very important, much important in the structural analysis, especially for the dynamic structural analysis. And we'll give you first the theory and the example of the usage of the problems. I mean, in applying the Eigen problem. Okay, and open this one. Okay, so start from the need of structural analysis. Yeah, for example, you can see here is the mobile here. Bank. Yeah, okay, so we'll see here for the first structure here. So this is the structure of red bar is the fixed, yeah, pure fixed, fully fixed, and the one is free. In the right one is free. So if, for example, here is the case of the swimming, yeah, for the swimmer jump the swimming pool, yeah, swimming pool, and then the people, for example, the people of the having the weight of P, yeah, P Newton, P kilogram, or etc. Yeah, and then there is a displacement D here. So if you put some weight here and force, for example, and then you will get D because there is a displacement toward downward. Yeah, and then what is K? K mean if you put P divided by D, here is K. So anyone have this two data of this, you can calculate the rest. For example, if you have the weight of the people here, and then you have a K, yes, the stiffness, right, stiffness here, and then you will get the D because D is P divided by K. Sometimes K is also K, and then T is displacement. Sometimes U. The notice the symbol, yeah, and also P sometimes F because force, because it's force. So this is the example of the case, yeah. Okay, how about if we try to turn this one in the left side, turn to the left side here, and to become this one, this side, yeah, because we turn, and not only one force, but this one, for example, 3, but it could be many, yeah, many, and we got n in many, yeah. For example, 100 stories building, yeah, you have to put this as one story, 100, for example, yeah. Okay, and this is the model of the structure that we can do to simplify. A model means simplify, yeah, simplify. Yeah. Of course, they will not capture all of the points, but they capture the main point, yeah, main point of the full structure itself. Okay, now we continue for having this structure. For example, this is the multi-structure structure, as there is 3 floors, yeah, 1, 2, 3, for example, and then you can lump this weight, the story here, to be M1 here, and this is for the second one here, yeah, for the second one here, can put here as a M2 here, and the last one here is the roof, for example, you can put it N. So this is the model, yeah, it's a very simple model, yeah. Okay, and then very simple model here, and there is a column, yeah, group of column here, support the system. So, for example, here for the first story is we put this as a K1. Second one is K2 here. Yeah. The third year is K3, etc. Yeah. So there are stiffness value of each of the stories actually. So if, for example, we put the force here, for example, earthquake. The earthquake forces can move forward and backward, yeah, forward and backward, and also right, left, right, yeah, and also up and down, the 3 dimension simultaneously, yeah. But we can get only one point, but one direction. For example, only the direction of right and left and right, yeah, right and left, like this one, yeah. So the moving like this one, and then if in case that one, we can simplify again that the force is the maximum force. So the dynamic force would be changed to assume to be the static force in the maximum value, for example, yeah. Because in reality that the force come from the acceleration of earthquake in the ground, yeah, the ground, the foundation, and then going up and then try to shake this structure, and the mass multiplied by the acceleration to become F, this one, all force. Yeah. Okay. And for example, if the force going to right side, so there will display the structure will displace in the to the right, yeah, to the right too. And this is the displacement of the story, the floor 1. This is the story of the floor 2, and then this is the displacement of the mass 3, yeah. MN, of course, if you would like to have more than 3. Okay. It could be the change of the movement of the change, the displacement to become like this one. This the people told this is the flexural mode in flexure, because it look like this one, flexure. But we use here as a shear displacement. Look like this is shear because of the shear force of this F1, F2, and Fn here. Okay. Next, this is only the one because in the reality, and if you try to design of earthquake in the building in the earthquake prone, you can do using PSHA, yeah, probability seismic hazard analysis too, and mean that there is analysis that if we have the subduction, yeah, subduction, or we have the for example, we have the subduction, or maybe you will have the potential of the earthquake sources, and then you can put and then make probability of to make the earthquake zones, or in the zones that have different, maybe they'll have the different degree of potential hazard of earthquake. So this is, you can also using the response spectrums method, yeah, rather in earthquake engineering, or if you take structural dynamic analysis, and then you will get one. Yeah. Okay. So bro, don't worry to turn your speaker off, yeah, because the sound will echo here. Okay. Next. Is that my voice? Some place there. Okay. Next, do. This is still sound. That. My sound? You? Yeah. Check sound. Okay. Turn in is off. Or it cannot be off. Okay, next. Because this force, the stiffness, as well as the force, the stiffness, as well as the stiffness force as and also maybe we will have also the damper too. Yeah. So not only one. Yeah. If one is okay, we use this equation. But if many, if this is many, so we use matrix instead of using only a constant value. Yeah. Okay, this is the example. There's the form of matrix of stiffness here, and then the form of vector or matrix of displacement, and then the form of the metric of force. So it becomes the operation of matrix. Yeah. If you operation of the metric, of course, you will familiar, yeah, using the simultaneous equation, for example, by using Gauss elimination to solve. So this is using the what we call matrix operation, yeah, matrix operation. Okay, then we start theory by saying the equation of motion. This is the equation of motion. And the free vibration, yeah, free vibration means there is no force here, zero. As for example, if the building, a building, yeah, got the shake by earthquake, and then earthquake stop, but the building still moving. Still moving mean still move mean until they finish, because there are damping. Yeah, there is damping to become smaller, and then finish to stop. Yeah, I mean, tomorrow I was in in the floor of 14, my office in Jakarta in BNPB, and got earthquake from Cianjur. Yeah, so when the earthquake stopped, but the building is still moving. It look like this now. Yeah, this means that free vibration. Yeah? Because vibration by free, there is no force. So in this equation here is this equation. There is a term here in the mass time acceleration. This is damping, yeah, damping ratio, damping value time the velocity, and then the stiffness time the displacement. Yeah, displacement. This is of course all are metrics, yeah, but we would like to skip this one for the damping value first. Yeah, the metric of damping will skip to study or to learn about the structure that vibrates naturally, or we call it free vibration condition. Yeah? Free vibration condition. Okay, next. Then from equation 3 to become equation 4. Yeah? Because we cross the, or we eradicate for a moment about the damper. So we got only the mass time, metric of mass, metric of acceleration, plus metric of stiffness, and plus metric of displacement to become zero. This is zero vector 2, yeah, metric of zero. Okay, and then if in this case we have the differential equation, yeah, differential equation, the solution of the such equation is the general solution is the function of, look like that this is the sine, because this is sine, yeah, and this is the form of a vector related to the shape of vibration. And then this is the amplitude of something that we could find or calculate after we have the data of earthquake, for example. Yeah. But in the general solution, we put the sine A and sine omega and T. Yeah, and then this is the u to become this one. Yeah, because there is a factor that related to the shape or form of a vibration that we call ladder is related to the eigenvector. Okay, and if we have found if we have now the displacement of cos, we can calculate the velocity and acceleration. Velocity is the first revision of displacement in the term of t. So from sine to become cosine, because there is a constant here to become here. Yeah, and because we have 1, 2, 3, 4, 5 until n here, and then to become acceleration here. How about acceleration? Acceleration is the first derivative of velocity of the second derivative of the displacement. So this is the first derivative of velocity. Yeah, mean from sine to become minus, from cosine to become minus sine. So this is minus to sine. Yeah. So if we compare equation 6 and 8 here, yeah, 6 and 8, acceleration and displacement. So you will get there's the relationship between the displacement of and the displacement and acceleration. Yeah, acceleration toward displacement. There is a equation. This is in a harmonic motion. Harmonic means look like sines. Yeah, sine, cosine is harmonic. Yeah, and you will study later if you take the dynamics, structural dynamics subject. Okay, and as we put to the equation 4 is the general equation. So all of the this is for the acceleration and mass, yeah, and this is the stiffness and displacement. Yeah, because this one, the A and sinus omega could not be 0, because if 0, so there is no motion. We would like to have a motion. So if this is not equal to 0, so something else, the rest is to be 0 here. Yeah, this is 0. Okay, or we call it, because there is a constant here, the vector of constant, yeah, vector, and then you put vector outside here, and then this is the equation. It's very important for you to know this equation. Later, yeah, but a second, a note. Later, yeah, from the equation 12 to become because we don't like to have a square, yeah, square, a form of this, so just replace the square of the omega here is the angular frequency square to become lambda. Okay, because just for a moment you make it more simpler, yeah, it is simpler, more simple, yeah, easy to handle. So to this from equation 12 to become equation 13. What does it mean if there is a this term equal to, because this is matrix. This is matrix. So you will have a eigen problem here. Why? There is eigen value. Yeah, this is eigen value lambda. Why? If you solve by using cos illumination directly, will not get it. You will stop. Yeah, cannot apply the cos illumination. Yeah, so we have to process to the next process, and then to continue to process to become handler, yeah, manageable. So the solution, call it eigen problem or hidden problem. Okay, and if you have the equation 13, yeah, equation 13 mean what? Mean that because this is the a metric equals to 0 vector, mean you have to the value of determinant, yeah, the two determinant. Determinant of this value here to become 0. So n 1, 2, 3, 4 until n DOF, yeah, degree of freedom. So if expanded of the equation free by polynomial with order n, so you can write down this one. This is called characteristic equation. Sometimes you usually by this one, yeah, and x n minus 1 plus x n minus 2, etc. Yeah, until constant equals to 0, for example. Yeah, but you replace x here by lambda here. So this is the characteristic equation, and you can solve finding x1, x2, x3, or lambda 1, lambda 3 by using, for example, if numerically, you can use the second method, yeah, Newton modified Newton-Raphson method. Next, then you will see the example here, yeah. This example is there's an example, yeah, example 7.1. There are two structures that could be model by lollipop, yeah, lollipop here, and this is the K, the stiffness of the story 1. This is the stiffness of story 2. This is the mass of roof. This is the mass of story 1. Actually, yeah. This is you assume that this only move from left to right, yeah, left and right, yeah, to left and right, yeah, not going other. So we put call here as a 2 degree of freedom, yeah, 2 DOF, because only 2 possibility of moving, yeah, there is freedom but only 2, and then put the equation here by using here the number, put the number in the for example, okay, I will try to split, okay, yeah, try to split to having here, yeah, mass mathematics here, and then you the question is how to find the eigen value lambda n and eigen factor of v, yeah, v n here. This is the equilibrium mean eigenvalue and eigenvector. Right? Is using random free, so using the equation of this, very familiar, yeah, familiar, popular in our case here. So just put the equation here, and then you put the number, yeah, put the number, because, but remember this is, there is a units, yeah, there is a unit here. For example, mass is 1 kilogram second square divided by centimeter, yeah. If K, stiffness, of course, kilogram per centimeter, maybe meter over millimeter, etc. Yeah, or maybe centimeter over millimeter. Okay, just put this number here to be in this one. For example, if this is in the case of the metric of K, so you will have this one, yeah. So you have the metric of K. So the metric is 3 minus 1 minus 1. This is the, we call it as a equation 1, yeah. Next, next for the mass, yeah. Mass, put the mass equation of the mass, yeah. Here, the mass here, put this value, and then you will get this one, yeah, the mass here. Okay, and then equation 13 to become, okay, this is equation 13, and if you put the numerical value all of this, so become this one, here. So this is come K, yeah, the metric of K. This is the metric of mass. Yeah. And remember, there is a eigenvalue here in the unit of radian square over second square. Yeah. Remember you have to be careful in the unit here. Okay, and then next is, yeah, so put together, yeah, together equation 13 here and solve by having this one. So if you have 0 here, mean, yeah, you have to determinant. You have to have the value of determinant of this value. Please focus here that determinant. I think you have to remember determinant mean this one times this one divided this one by this one. Yeah. Okay. So 1 by 1 first. Okay. Step by step. Yeah. This one here is this one. This one multiplied this one. Yeah. Okay. And then second one, the color is green. This one times this one minus, of course, yeah, this one. Be careful that you have to have this one minus it. Yeah. Minus. So minus the violet, yeah. And then minus the green one here. So what is the result? The result is this one. So you have the polynomial equation, this one. So maybe you are familiar with this one by using 2x squared minus 5x plus 2, yeah, equals to 0. Usually is one x, but now lambda, because the symbol of eigenvalue is lambda, that is related to the angular frequency square of the vibration. Yeah. Next, so if you have the quadratic equation here, so you can solve by using ABC rules, very much famous since you go to the senior high school, yeah, junior high school, high school. So you will have the two value, lambda 1 and lambda 2. Usually we use x1, x2, yeah. So because there are two solutions here, plus and minus. And then this case, the solution is, if we call it N1 ladder to become related with the mode 1 of vibration, mode vibration 1 is the lambda 1 here, yeah. So using minus, yeah, so we have 0.5, and then second using plus here, the plus sign here, so we have this one N2 related to the mode of 2, the second mode of vibration, yeah, to become lambda 2 is 2. So there are two eigenvalue here. All right, already you have two eigenvalue, yeah. Okay, and then eigenvalue here. Next, you have to find the eigenvector Vn. Vn here, Vn. In this case, you have Vn mean 1 and 2. 1 mean in the floor of 1. This is the roof. The other one is roof. You put later the roof to become 1. 100% mean 1. Yeah, to put substitution, because this is the just comparison. So the later, if you would like to see the how many centimeter, for example, to move your ladder, you will have, if you have the data of earthquake move, or you have data of force. Yeah. Okay, and 1 is equal to a half, yeah, a half, 0.5, and put in the equation this one, equation 3, yeah, put the equation 3. So if you put the equation 3 become this one, yeah. Oh, sorry. Okay. Equation 1, 3, yeah. To pick up equation 1 here is this one, yeah. And then lambda here is very important. Lambda here is the first eigen value is half, yeah, 0.5. And then this one, so the mass, you have this one, yeah. So remember that you have to find this eigenvectors here, okay? Okay. I have to clean up. Then after you have this one, okay, I put this one also, example. Okay. So you have actually have two equations here. Two equations. What is the equation? The first is this one, type this one. So it one to become this one. Yeah. The value here. Yeah. This and this one equal to this. Yeah, remember that the operation of the matrix is the horizontal and the vertical. So 3 minus 1, 2 times 5, 1, 1. Yeah. 1 in the mode 1 and then in the first 4. Yeah. And then 2 mean rows. Yeah. And the minus 1 is this one. Yeah. Okay. Actually, we have another equation here. Yeah. This is the second equation. This one times this one. Mean here, this one times this one. Become here. Yeah. This one times this one. To become this one. 0, of course. There is 0 here. Okay. So this means you can find the y here is 0.5. Yeah. What does it mean? Yeah. Mean is, I have to repeat this one because maybe this is the critical thing that you have to know to understand. This one is, the first equation is this. Have this mean, I have to put here this one time this one is 1 here. Then okay, here this one type this one equals to this one. Yeah. And then what about this one? Here is equal to here. Yeah. Okay. So we have the rest similar. Yeah. I have already explained. So there are two equations that should be similar. So the eigenvector is because what we assume that the one of them are 1. So to become this one is 0.5, yeah, 1.5. How about the second equation? Second mode we call n equals to 2. Yeah, equals to 2. Again, we put here this one. Yeah. So again, in the mode of the second mode, you put this one too. Yeah. Here is the stiffness, this one. And this one is the mass here. Yeah. Mass. Then you have to put the red line. Remember, there is a lambda 2. Yeah. Lambda 2 means equals to 2. Yeah. So we solve because we can solve, yeah. 3 minus 4, for example, 2.2 here, yeah. Okay, wait a second. I have to clear now. I have to move here, yeah. So this minus 2 times 2 means 2.24 here. This is this one, yeah. And then minus 1 plus 0 equals to minus here. Okay, but I use the different color. We'll use different color. So minus 1 minus 2 times 0 equals to 1. Yeah, minus 1 here. Okay. Next. Yeah, and then of course this become 0, 1 here. Yeah. Okay. I try to solve the numerical matrix of this side, yeah. Okay, and this one, yeah, minus this times this equals to -1 here, yeah. Okay, and then next, this one -2 -1 here to become here, yeah. Okay, this already here, yeah, come 1 because we assume that the roof move as 100 the references, reference, yeah, space line, space reference point, Okay, next, zero is n is equal to this one, yeah. So we have to solve. Here, yeah. Solve this one is actually there are two equations again. What is that? What are they? Yeah. The one is here. This one, yeah. 2 times this one. Yeah, 2 times this one equals to this one. Then thirdly is times this one equals to this. Yeah. Okay, what is 0 here? 0 here is this one. Okay, we have the different color. 0 here is so mean minus P 1.2 to become 1. So 4.2 become -1. Okay, there are because there are second two equations, so we have to check the other. The other should be the second equation here. For example, here, yeah. So this is the second line here. This one, yeah, times this one. This is here. Okay, yeah. I will use the different color, and I have this one times this one equals to this one. Yeah. Okay, and then next, the last one is how about 0 here? Because this is second question. 0 here is this one. So phi 1.2 is -1. Yeah, and a chord similar. Yeah, in Indonesian we call cocok. Yeah, matching. Okay, in accordance. Yeah. So if you write down of the equation of the eigenvector, yeah, phi 1 is this one. Yeah, 1 is the reference, -1 is this. Oh, here. Oh, it should be 2, yeah, phi 2 here. Okay, let me check. That's right or wrong? Oh, I have to. This is the phi 1. Ooh. This is the phi 1 is 0.1 here. So there are 2, yeah. 2 here. So -1. Yeah. Okay. So what is the physical meaning of this one? Of the eigenvector and eigenvalue? Yeah. Okay, first from the eigenvalue first. Yeah. From the eigenvalue mean lambda n. The n here. Here is lambda n. Is the equals to the back to the simplification before. This is the angular frequency square. So lambda n. So frequency angular frequency mean the root of lambda n. Yeah. Okay. No, got that now. Secondly, then okay. So the Fn, what is Fn? Fn is frequency, yeah, the linear frequency. Yeah. It's not angular frequency, but linear frequency. Here is the phi n plus phi to 5. This is the formula. Yeah, and in hertz. Yeah, hertz mean over second. So the period of natural period of a mode, for example, for n or 1, 2, 3 of the building is the over power of Fn. So just opposite with Fn. So 1 divided by Fn means second. Yeah, 1 second in second. Okay. Yeah. So and then what is the n here? Is the natural period here. G is this one. Yeah. So if there is motion, this is the time. Yeah. This time, this is the displacement. Yeah. Because this is basically displacement. So this is like using sine or sine this one. Mean Tn is from the peak to peak here. Yeah. S is similar to this one too. Yeah. Because this is harmonic motion. So T here is this one, the natural period. So 1.2 point in 1 second cycle of vibration. Yeah. Again, how about the eigenvector? Okay, first eigenvector, what? This one. Yeah. First eigenvector is this one. Mean what? First eigenvector is this. Mean here is the reference is 1. Yeah, and then the floor here. This is first floor or zero ground. Yeah, floor is 0.5 here. Yeah. So if this is the moving, for example, if they move 1 meter to the right, for example, this one, the right 1 meter, mean this one 0.5 meter, because this is the just comparison, yeah, relative. Next, if, for example, the building move to the left side here, minus 1.5 meter. So this move 0.75. A half only, this is the half. So this means that eigenvectors for the first move, because yeah. Later, if in the last time you will go to my museum, yeah, in Arctic Museum, Kalura, not far from here, but it's very cold there. Yeah. And also maybe rainy. You have to use the jacket too, yeah, to using the thick short, yeah, or using the jacket, etc. You can do that, and using the plastic coating, yeah, for to anticipate if the rain. There is a you will see there. It's very simple to know the mode 1, mode 3, and the concept of modes, the concept of eigenvalue. It's very easy because you will practice there. And you would like to see too, there is a practice using Simutaga for numerical computing in the YouTube, my YouTube. Just type Simutaga Numerik Sarwidi, you will find there. Okay, next. For the second, now for the second, the last one, yeah. For the second eigenvector, here is the second eigenvector that I mean. This is the second eigenvector. The numbers 1 is the references, because it should be in the roof. 1, put here is 1. And how about -1? -1 is the moving, the comparative moving for the floor in the middle here. Yeah, it's -1. Okay, and if, for example, the building move here 1 meter, so if the building here moves -1 meter to the left. So in the moving, if the building move on the east 1 meter, so the second floor here move to the west 1 meter, because this is the comparison. If, for example, the building move 105 here to the west, to the left, 105 here minus, yeah, and then the building here move also 100.1.5 meter to the east. So the building will move like this one. Yeah. So there is inflection point that is 0 here. Yeah. Okay. This is the meaning, the physical meaning of the eigenvalue and eigenvector. So if you look back to see the complete picture of this is here. Yeah. This is the complete picture here. So you have lambda 1 compared to the T1 here. T1 here. Then lambda 2 is related to the T2 here. So become smaller. Yeah. The shorter period. The first is the longer period. Okay. And and this is the motion. This is the time. And go to the right here is time. Yeah, second maybe. Yeah, it could be. And how about the roof? The roof moving is this one. The roof moving this one. The blue one here. Yeah. One here. On the first mode. And then how is the second floor here? Floor here. So they move a half of this. Yeah. So the red dash here. Yeah. This is on the first mode. How about the second mode? Second mode means the roof here move 1. So move here. Yeah. 1 here. And the T2. Yeah. The blue one here. Blue curve here. And then how about the second floor here? Because this row second floor here, because -1, so opposite direction. So this opposite direction. Here. Yeah. So the red one here, so opposite direction. Yes. I think it should be finished. Should be finished. My explanation. If you have any question, please raise. Yeah. Can discuss. Yeah. Okay. So write down in the setting. Okay. Writing and setting. Yeah, in the setting. Okay. Okay. Yeah. Okay. Yeah, write down the setting. So I have to close the Zoom because it is finishing. Yeah. Okay. We have to finish this session.